I am really hoping that third time is a charm on this, on exponential functions. I have tried this twice. I have failed twice. Anyway, if there's a mistake on this, we're just going to have to look down to the comments and hopefully get it ironed out from there. Okay. Right, exponential functions today. Exponential functions. First of all, this X right here, I can plug any real number I want to into it. Okay. I've got a couple of rules for the A and the B. The A, I'm going to be calling the initial value today. Whenever I'm looking at this initial value right here, A cannot equal 0. Well, that makes sense. If A was equal to 0, it would zero out the whole function. I wouldn't even have anything. B is going to have to be a positive real number. So not only am I wanting B to be positive, I also don't want it to equal 1. If B equals 1, it gives me a constant function that will not work. The big thing I want you to see, though, with this is that, sorry about this over here, is that the x is in the exponent. And that's how I know if I have an exponential function. So looking at these, the only ones that have x in the exponents are going to be my exponential function. Looking at A, well, I have a 4 in the exponent. That's not an x. The x has to be up there. So on part B, I'm good. The x is in the exponent. Even if other stuff is in the exponent with the x, I'm good. And on part D, x didn't make it to the exponent, so it wasn't needed. So that's the big kicker today, is to see that x is in the exponent and see what little changes we have to make there. Now, just like we've done with every other function, we can evaluate functions at certain places. For instance, f of 7. F of 7, I'm just wanting to plug in 7 in for x. Now, some of you are very good at making a calculator screen look like that. It does the order of operations for you, and poof, you get the right answer. I'm going to go ahead and show you step by step what's going on with this. 7 minus 2 is 5. Common mistake on this is people do their multiplication before they do their exponents. I've got to take care of that exponent first. So I get 2 to the 5th is 32. And finally, a negative 96. So I want you to work part B and then pause the video, then work part B and see if your answer appears on the screen. Be super careful with those parentheses. I'm raising that negative 2.2 to an even power, so that negative goes away, and I get positive 1.71. Just for ease, I'm going to round everything in this video to 3 decimal places. So let's talk about the B. I said earlier, A is going to be my initial or my starting value, but this B right here is going to be my growth factor. It tells me how fast my exponent is growing. So I've put an example over here of f of x equals 2 to the x. Well, you might be saying, well, it's missing its a. Well, no, the a is 1. So its initial point on this graph would be down here at 1. And then whatever's being raised to a power, in this case 2, just tells me how fast this graph is going up. It looks a lot different than other things we've graphed this year, just with how fast it's increasing. So that 2 just means that after every unit right here, it's doubling to get to the next one. Right? It just keeps going up. So that's called my growth factor. And we're very interested in that growth factor when we talk about population growth or a number of things that happen in real world phenomena. So like the population of Dexter in 2009 was 7,601. I think that is a real number and is growing at a rate of 0.6% annually. I don't think it's growing quite that much. So I've taken some liberty in here with some of the numbers just to make it so it comes out. So that's going to give me a growth model of P of t equals 7,601 times 1.006 to the t power, where t is the years since 2009. That's the big thing I want you to see with this, is that t is years since 2009. So the fact that I'm using t equals 0 does not mean I'm going back 2009 years before 2009. I'm going to look at my years that I have in these equations, and whatever my smallest one is, I'll let that equal 0 and represent represent t equals 0. That will help keep these numbers calm down a lot. So using this growth model, what is the current population of Dexter? Well, I am currently making this video in the year 2018. I'm missing some numbers. 2018. Well, 2018 is 9 years after this 2009 year. So that means that to find the current population, I need to plug 9 in for t. So I'm just evaluating another function. So I've got a little bit of math to do there. I think it bumps me over the 8,000 mark. If I remember correctly, it's 8,021 people. I'm going to let you guys work the second part of this, where it asks for the population in the year 2030. Go ahead and find your t value, plug that in, and then hit play once you get done. T in that case is equal to 21, and we get 8,618 people. Now, we're not always just gifted a nice equation like we have been. Sometimes we're not given an equation, and the whole point of the problem is coming up with our own equation. Okay. Now, there's two ways that this can happen. First, they could give you this initial point right here, the initial value. And if they give you that initial value, just like we saw on the last slide, that initial value slid right here into that front space where this A is. We like those problems. We can then take our other point, x, y, plug it in, and solve for B. Now, it gets a little bit harder whenever they do not. Neither of the points take on this form 0a. You have to end up using a system of equations to find A and B. Either way, though, what I want to point out is that we are looking for both points, A and B, the initial value and the growth factor to plug in to get our answer. So let's see a couple ways this will work. So I'm going to kind of work this Dexter problem in reverse. I chose a different year just so we could play with some different numbers. However, I left t equals 0 to be my 2009. Again, I'm looking at 2009, I'm looking at 2016. 2009 came before 2016, so that takes on t equals 0, okay? Meaning that 2016 would be t equals 7. So the 2 points I get from this are 0, 7,601. Watch me on this number right here. I've messed this up on the first video, that's why I'm redoing it now. And instead of x, y, I'm going to attempt this problem with t's and p's, time and population. And so my second point would be in 2016, when t is equal to 7 years after 2009, it tells me the population then was 7,927. Probably just another number I came up with. Try to keep the same growth factor though when working this. Growing exponentially, I want to know the p of t. I want to know the function that I can write. There I go again, writing y's. Right. So my population is a function of time. Well, if I know what the 0 is, this is my initial population from the get-go, this 7,601. I can take it and just plug it in for my A, my initial amount. And then it tells me a random other year. I chose 2016 on this. So that tells me that the population that was 7,601, after it followed this growth factor for 7 years, it grew up to the point of being 7,927. I just have a problem. I want to solve this for B. Now, be careful there. I am actually not going to put anything in my calculator until the end to help get a more specific answer, not taking a rounded answer of a rounded answer. So right here, I need to take the 7th root of both sides. I'm going to need to consult the calculator on that. Actually, I remember what it is. It's going to be the exact same growth factor I had on the last slide. You can double check that for me if you want to. So the good news is I have my A, I found my B, I'm ready for my final answer. my population is going to be based off this initial population times the growth factor raised to the number of years. And this will tell me the population of Dexter at any year that I need, based off of t equals 0 being 2009. I do want to play with this graphically just a little bit, and then I will be done. So I'm going to make up some points. That doesn't always work well, but for these, I think it'll be okay. I'm going to avoid green. So I'm going to choose the point 0, 2. And then let's come over here. I think someone did like -3, and 1, 2, 3, 4, 5. That worked well a while ago. -3, 5. So as you can see on this one, my line is going down the other way. No big deal. That means instead of the population growing, it's decaying. That happens a lot in chemistry and endangered species, stuff like that. So, write an equation for this function. So I'm just going to start with my a, b to the x. Hopefully you're tired of seeing that by now. That would be my goal. And again, I do have an initial value. Be careful. Your initial value has to have 0 right here in this position. So this is like saying after 0 years, my population was 2, or whatever we're modeling. So that 2 can come over and land right in that same spot that my initial population did on the last example. From here, we were giving another random x and y. So I'm going to plug 5 in for y, -3 in for, oops, so my b, not my b, 2. B, and then -3. Several ways to solve this for B. One way that I want you to be careful with is that these negative exponents I've seen today throwing a lot of students off. So I'm going to go ahead, my first step is and relieve this equation of negative exponents. Now from there we have a personal little trick that we learned about in my class called moving the hat, or we can just multiply both sides by b cubed, and then b cubed is equal to 2/5. I've almost got my hands on b. I just need to take the cube root of both sides. And so the cube root, let's see, math, cube root of 2/5 comes out to be 0.737, I do believe. Okay, good news. I got my b. My a was given to me. So I can write my function. Y equals 2, 0.737 to the x. So like I said, that's not too bad. It does need some practice given that initial value. But what happens if we're not given that initial value? Let's see how that comes out. Not given that initial value, I'm just going to make up some points. Oh, let's come up here at 3, 7. And the point -2, 1. So if I was to draw that, try to keep a constant growth rate on there. Oops, I missed my dot. Heavens. Act like that goes through it. No big deal. We got the 0.37. Okay? And as you can see, this y-intercept this time, my initial value, I'm not too sure of. Just with my drawing, it looks like it lands somewhere between 2 and 3, but I can't even be sure of that with how close it is, and not sure if I actually went up by that constant growth rate. So what I'm going to do on this is I'm going to write out y equals ab to the x twice. I'm going to do my best to color coordinate this, and there's going to be some crazy arrows going around, so please stick with me. And what one of these equations is going to do is it's going to give me my initial value, while the other equation is going to give me my growth factor. Let's go ahead and plug in what we can on this. I don't know A or B on either one of these, but I can plug in for X and Y on those. So this equation on the left, I'm going to use the point on the left. 1 equals AB to the -2. For the equation on the right, I'm just going to use the point on the right. 7 equals AB to the third. And from here, it doesn't really matter. Just pick one or the other and solve for A. I'm just going to choose the left side since I think that'll make it look nicer. I've got that negative exponent happening again. I'm going to go ahead and first relieve myself of that so I don't have to worry with it. Multiply both sides by b squared, and I have this solved for a. Unfortunately, it's not a number yet, but it will be very soon. So b squared equals a. Now what I'm going to do is I'm going to take this b squared equals a. I'm going to take this b squared, and I'm going to switch sides, and I'm going to plug it in. Since b squared is equal to a, I'm going to do a direct substitution right here. I'm going to get 7 equals, instead of a, I'm going to write b squared. And so I'm going to end up getting my growth factor first. 7 equals b to the 5th. Take the 5th root of both sides. And I'll have to do that real quick. 5, oops, 5, x root of 7. Got 1.476 on that growth factor. 1.476. Again, excuse my arrows, but now that I know b, look how much easier it is going to be to find a. Because a is simply defined as whatever b is squared. So I'm going to take that answer I just got, the 1.476, and square it. And so 2.179. 2.179. I got pretty close on there. 2.179. I wasn't that far off. That's my A. I've got my A. I've got my B. That is the beef of the problem. I'm writing a little big. Oh, I squeezed it in. And that would be my answer. This will take practice. Stick with it. Follow these examples. And good luck on the homework. Let me know, as always, if you have any questions.